In this video, we'll dive into agentic design and implementation. This is where I'll walk you through how the agent is structured, the decisions behind its architecture, and the key steps in implementing it. In a later video, we'll discuss lessons learned from the process. I'll highlight the challenges faced, the solutions applied, and the insights that could help with future projects. If you're interested in exploring the code in detail, you can find the complete repository at the link provided on the slide. Now let's take a look at the core packages that Ava leverages from the LangChain ecosystem. First, we have LangChain itself. This is a powerful framework that simplifies the development of applications by integrating large language models with other data sources and APIs. It allows for the creation of context-aware interactions, making it a crucial tool for building intelligent applications. Next, there's LangGraph. This open source framework is key to developing stateful multi-agent application. It enables us to construct workflows where large language models interact with each other in a coordinated manner, providing fine-grained control over agentic processes. Together, these packages provide the foundation for Ava's intelligent and adaptive capabilities. Let's walk through the high-level process flow of Ava, represented as a finite state machine. The flow starts at the uninitialized state. This is where the agent has not yet begun its task. From there, we move to the puzzle setup. In this stage, the agent prepares the environment, loads necessary resources, and initializes the puzzle-solving process. Next, we enter the puzzle-solving state. This is a key step where the agent actively works on solving the problem. As you can see, there is a loop here, allowing the agent to iterate through this phase multiple times until a solution is reached. Finally, we arrive at the puzzle complete state, signifying the task has been successfully completed. In essence, this graph highlights how agent progresses through different stages in a structured finite sequence of operations. On this slide, we're looking at a visual representation of the Ava workflow using LangGraph. This diagram breaks down how the different components interact and flow through various stages. LangGraph, as represented here, uses three primary visual elements. The yellow ovals indicate nodes in the workflow. Solid black arrows represent standard edges connecting nodes. Dashed arrows represent conditional paths that can take different routes depending on the logic. The process begins at the starting node labeled Start. From there, it moves into the Run Planner node, which acts as the central planner. This planner has connections to multiple downstream tools as indicated by the arrows. The planner's job is to manage which tools are executed and when, based on conditions indicated by the dotted edges. Each node, such as Setup Puzzle, Get Embed Vec Recommendation, Get LLM Recommendation, Get Manual Recommendation, and Apply Recommendation, represents a specific tool used in the workflow. These tools perform discrete tasks contributing to the overall workflow. Finally, the workflow progresses to the end node, signaling the completion of the process. This path can vary depending on which tools are triggered during the run. This visualization helps break down complex workflows into a modular, manageable parts. I'm going to walk you through the Ava Planner and how it manages workflow sequences through the use of a large language model. This slide shows the structure of the prompts used with the LLM. On the left, we have the system prompt, which serves as the foundation for how the Ava Planner operates. The goal here is to determine the appropriate next tool based on the current state of the workflow. The list of tools available include Setup Puzzle, Get LLM Recommendation, Apply Recommendation, Get Embed Vec Recommendation, Get Manual Recommendation, N. The prompt also emphasizes the key factors that influence the decision-making process: puzzle status, tool status, current tool. Finally, the system is expected to provide its output in JSON format with the selected tool as the value under the key tool. Now shifting to the right side, the user prompt guides how the selection process works in practice. The instructions highlight important conditions. For example, if the puzzle is not initialized, the setup puzzle tool is used. If the puzzle status is puzzle completed, the workflow ends by selecting the end tool. The table shown here helps match the correct tool to the current workflow state based on tool status and current tool. For example, if the current tool is setup puzzle and the status is initialized, the next tool will be get embed vec recommendation. If the tool embed vec recommender has the status have recommendation, the next tool will apply recommendation. Additionally, if no tool can be selected, the fallback option is to use the abort tool. Let's take a quick look at the AVA planner. The function runPlanner drives the next step in solving puzzles by managing workflow instructions and updating puzzle state as described in the previous slide. It starts by retrieving and logging instructions, then converts the puzzle state into a readable format. This information is sent to OpenAI's GPT 3.5 Turbo Large Language Model to determine the next action. The temperature parameter is set to 0 to ensure deterministic operation of the workflow. The function updates the state based on the response, ensuring the process continues smoothly. In the end, the updated puzzle state is returned, ready for the next step. This slide breaks down the code structure, focusing on the integration of LangGraph to manage decision-making processes. Let's explore the main components. Starting with the runPlanner function, this serves as a LangGraph node. It takes in the current puzzle state, logs the entry, and serializes the state into JSON. Here we add the JSON state to be part of the prompt for the LLM. The critical part happens at this line, highlighted here, where we call the function askLLM for next step. This uses GPT 3.5 Turbo to determine the next action with a temperature of 0, ensuring deterministic behavior. Now let's move to the determine next action function, which acts as a LangGraph callable. This callable evaluates the state to decide which tool to trigger next. It extracts the tool to use from the state. If the tool is abort, it ends and raises an error. If it's in, the process terminates. Otherwise, it returns the selected tool to continue the workflow. Next, we define conditional edges. This section maps potential actions like setup puzzle, get LLM recommendation, or apply recommendation to their respective nodes. Depending on the tool chosen by the LLM, the workflow transitions to the appropriate node dynamically. Here on the right, we visualize the flow. The process starts at runPlanner. Based on the tool selected, the next node, such as setup puzzle or apply recommendation, is triggered, guiding the overall workflow. This approach allows for flexible LLM-driven decision-making in the AVA planner. By integrating LangGraph with LLMs, we create a structured yet adaptable pipeline that can handle complex decision trees, enhancing automation and efficiency in planning tasks. We now shift our focus from AVA's planner to AVA's memory by describing the core data structure and the key attributes that controls AVA's behavior. On the left, you see the definition of a puzzle state class, which contains various attributes used to track the state of the puzzle solving process. Here is a brief summary of the attributes. We start with the puzzle status, puzzle tool status, and current tool, all of which are string attributes that keep track of the current puzzle state and tool in use. Vocabulary DBFP is the file path to the SQLite 3 vocabulary database. Tool to use specifies the next tool in the workflow. Words remaining is a list of puzzle words that need to be grouped. This is initially populated with the 16 words. As correct groupings are found, those words are removed from this list. Invalid connection hold tuples of word groups known to be incorrect based on what the connection puzzle responds to a suggested group. Recommended words and recommended connection provide the suggested grouping with the proposed connection. Flags like recommended correct indicate if the recommendation was correct. The recommendation correct groups attribute is a list of correctly grouped words. Recommendation answer status is used to provide the response from the connection puzzle to a suggested group. Flags such as found yellow, found green, found blue, and found purple signal if specific color-coded groupings have been identified. Mistake count and found count track errors and correct groupings. LLM retry count is used to control the number of times the LLM is allowed to make a guess. Recommendation count is the overall recommendations made by AVA. LLM temperature controls randomness in the language model's output. On the right, we call it the key attributes that drive the workflow. These attributes collectively ensure the AVA system can iteratively solve puzzles by refining its recommendations, tracking progress, and learning from mistakes.